My topic is first result on a laser guide star wavefront sensing prototype for the ELT. And we all know there are three important components in AO system. The first one is the wavefront sensor. It acquires the wavefront from the object, which is distorted by the atmosphere. And the second is real-time computer. It acquires a wavefront to output the control signal. And the third is deformable mirror. It uses the signal to correct the wavefront to get good qualities images. So the wavefront, how to measure the wavefront is one of the most important components in the AO system. When measuring the wavefront, we need sufficient photons to get higher signal to noise ratio and to keep the estimation error low. It's often difficult for us to find a natural guide star, so we get the shine laser up to the space. But this will bring a problem because when the laser irradiates the sodium layer, which is 19 kilometers higher and has a given width of 20 kilometers, the illuminated area is not a point source. On the detect plane, the spot will be elongated with the further distance from the launch site like this. This phenomenon is called the elongation. And in details, we can see in this image, the spot will be elongated to 25 arcseconds. If we use 1 pixel to cover 1 arcsecond, we need 25 pixels to cover such a elongated spot. And if we use 80 by 80 aperture, we need 2000 by 2000 pixels to catch the whole image. But such a big detector running at 500 Hz without noise less than 3 electronics does not exist. So in this work, we study the possibility to use a Sony CMOS detector with 1100 by 1100 pixels, and at the same readout noise, and the frequency is 480 Hz, and with a global shutter. In order to reach our goal, there are 3 steps to be divided. The first step is to configure an initial system. It includes the source, lens, and the detectors. And we make the linearity test, and the steps we will add the optical relay and the lens slate to start the wavefront sensing. And in the 3 steps, we measure the elongation and add the phase screen to make a full-scale test. So this work is to develop a prototype to experimentally validate a full-scale version of a laser guide star wavefront sensing for the ELT. And before we configure the system, first we set up simulation tools to guide us to choose suitable methods and parameters, and to establish parameter experiment. Here we use Shark-Hartman sensors, and we also measure the 2 of the important noise. This is a photo noise and the readout noise. We can see in the simulation there is a good image. If we add the photon and readout noise, the image will be distorted. And we also test the relationship between the flux and the pixel variance. And we also test the impact of the undersampling. We measure the size of the sampling spot. We can see this image. If we enlarge it, if the full price at half maximum is below than 1, the undersampling will occur. And according to the comparison between the relationship between the real position and the measure position at different full widths at half maximum, we can see when we choose it is equal to 1 pixel. This result is good. So the undersampling of the image introduces a limitation of the accuracy. After the simulation, we began to configure the bench. We choose the spot size as 1 pixel, and our goal is to use 9 micrometer equal to 1 pixel. But according to the magnification factors of the lens, the 360 micrometer source doesn't exist in the market currently. So we use 400 micrometer source to produce 10 micrometer spot now. But this does not affect the measurement of the parameter of the detector. So we configure the initial system like this, and at first we measured the pixel linearity. We moved the spot by steps of 0.1 pixel within the range of 1 pixel. We can acquire a good linearity of this camera. But now we just acquire the spot like this. It's not exactly less than 1 pixel because the source used so far is not the final one. And we also measure the cosmetic defect of the camera, and this image is background in the laboratory, and there it shows there is no bad pixels, so it has a perfect cosmetic. And we also test another important parameters about the camera, that is the readout noise. And again, we tested the photon transfer curve at different areas on the image, and we averaged the value and acquired the average readout noise. And again, and we compared them with provider spreadsheet. They are sorry. The result is very consistent, and we also compared them with detector-to-detector tests, which is done on 10 chippers by Jean-Luc Gache. It also the results also are very consistent. And another important noise is photon noise. We measured the centroidin accuracy and in different levels of flux. We can see this is a lower flux, medium flux, and high flux. It corresponded to this image. This is a relationship between the flux and the pixel variance, and we test the two direction. When we use the center of gravity to measure such images, it shows a basic linearity, but it shows fluctuation in this in the center of gravity methods, but if we use the weight of center of gravity, when we choose the radius of the mask, it shows a good linearity. So it's better for us to choose a weight of center of gravity to do the test. And after talking about, it's difficult for us to decide if the initial system is good or not. So we group the photon and the readout noise and compare the real measurement with the theory and the simulation. At first, this image shows the theoretical two noise. This is the green line is this two noise, and then we make the simulation in two direction. It shows a good match, and if we use then we add the measurement in the image, we can see it has a good match in the medium and the higher flux, because this theory is not very suitable for the lower flux, and the irrelevant pixel can have the effect on the central reading calculation. So we can see in the lower flux it has a big fluctuation. But if we choose the weight center of gravity, we can show we can see it also has a good match, and especially in the lower flux, the fluctuation was eliminated. That is to say, the mask can eliminate the impact of the irrelevant pixel on the central reading calculation. So at this time, we can say the system now it has a good performance to do the continued tests. And about the calculation, now we have configured the initial bench, and we also measured the pixel linearity and compared the real measurements with the serial and the simulation. It shows a good match, and the next step is to test the line spirit function measurement to acquire the pixel response. And another part is compare the global shelter with the rolling shelter. And the second step is we expected it to be done in the end of this year, and now we have the optical relay and the micro lens. Then we will get the add the two parts to make the wavefront sensing. And the step 3, we will add the phase screen to make a full-scale test about the elongation. That will be expected to be done in the spring in next year. Okay, that's all. Thank you for your attention.